as a prerequisite to being good at related rates, we must be able to identify which variables are changing and which are not. So before we even get into related rates, let's talk about identifying variables and rates of change. The radius is changing at 5 meters per second. Look at the units, meters per second. That's a rate. Now, one of the things that we have to get in our minds is that rates are, when we take a derivative, remember what we're doing is we're finding the slope of a tangent line. That's y per x. It's a rate. For every unit change in x, we get so many units of change in y. It's change in y per change in x. It's a rate. So when we say related rates, we are really, it's a disguised way of saying we're talking about derivatives. So look at the units, meters per second. We know that that's a derivative or a rate. So we can say dr, the change in radius, per dt, the change in time. We can think of those d's as delta. Here's our Greek letter delta. Change in y, delta y. Change in x, delta x. Well, dr dx can be thought of as delta r, the change in r, per change in time is 5 meters per second. Notice that's a derivative, that's a rate. The water level in a cylinder is 8 centimeters. Well, maybe the height of the cylinder, the height of the level of water in the cylinder is 8 centimeters. So maybe we just say h is 8 centimeters. Notice the units. There's no rate there. It's not something per something, something divided by something. The area is changing at 10 meters squared per second. So dA, change in area per change in time, is 10 meters squared per second. Notice, some unit divided by some unit of time. Then we have a rate. The derivative dA dt is 10 meters squared per second. The water is drained from a cylinder at 5 cm cubed per minute. Well, that's a rate. So dV dt is equal to, because it's being drained, it's going down, we have a negative rate. Negative 5 cm cubed per minute. Continuing on, the radius is 5 meters. Well, that's not changing, so r equals 5 meters. Look at the units. We have no units per other units, and the denominator being some unit of time. So this is not a rate. The length of a rectangle is 10 centimeters. Length is 10 centimeters. That's not a rate. The balloon is being inflated, so it's increasing. So look at its units. Cubic units, that's volume. So dV dt is positive 10 cm cubed per second. Notice when we're deflating or draining, the rate is negative. But when we're inflating or filling or making it bigger, then we're saying it's positive. Note, dV dt means the change in volume per change in time. The width of a rectangle is increasing at 10 feet per minute. Well, this 10 feet per minute is dW dt. It's a rate, it's a derivative. A ladder is falling at 8 feet per second. So the height of the ladder, dH dt, is negative 8 feet per second. Notice that's a rate, dH dt. The height is changing with time, delta h over delta t. The area of a triangle decreases at 1 foot per second squared. Well, this is dA dt is negative 1 foot squared per second because the area is decreasing. When a quantity is decreasing, then the rate will be negative. A boat is traveling at 10 miles per hour. They just gave us the rate. How far has it traveled in 4 hours? Well, these are these dirty problems. Distance equals rate times time. Almost looks like it says dirt to me. So how far has it traveled? That's our unknown. So distance equals the rate, which is 10 miles per hour times 4 hours. Look at the units will cancel, and we can say with confidence that it's gone 40 miles. Sorry, I screwed that up. 40 miles. So distance equals rate times time. If a car is 400 miles from the house, moving at 80 miles an hour towards the house, how far will it be from the house in 2 hours? So it's going to be closer than 400 miles. Well, if we take 80 miles per hour and we multiply this by 2 hours, notice those units cancel, and we get 80 times 2 is 160 miles. So then 400 minus 160 gives us 240 miles from the house. How do we solve related rates problems? Now that we've had an idea of what these rates are and what are the differences between rates and just constants, like the radius is 5 meters. Well, if it's not changing, then we say r is 5 meters. Solving related rates problems involves 7 steps that you'll get quite good at if you just get a little practice with this. 1, read through the problem and draw a picture. So important to draw a picture. And even if you think you don't need a picture, draw a picture. Assign symbols to all of the given information. So draw a picture and then label your diagram. Determine which variables are changing and thus have rates or derivatives. Look at the units as we've done. If you see some unit divided by some other unit, that's a rate. Determine which units you're solving for and which variables you're solving for. Not so much which units, but which variables you're solving for. Here's the key step. Write an equation that contains all of the variables. So you have to bring some knowledge to the table. And then substitute numbers that do not change. So they might give you some constants that we can substitute in. Take the derivative of both sides after you substitute for the constants, and take that derivative with respect to time. So our denominator of our derivative will be dt, change in time. And then plug in all the given values and solve for the unknown. Those are the 7 steps we'll take.